Hi, and welcome to Knots and Surfaces Introduction to Topology. I'm Fedor Duzhin, and I'm going to be your course instructor. Today's lecture will be online. The rest of the lectures will be real lectures in class. So here is the plan for the day. Today we have some very big and exciting plans, and our main goal for today is to prove an actual theorem in topology, and it's going to be a difficult theorem. So theorem about classification of compact closed surfaces. Okay. Now, knots and surfaces are studied in the mathematical discipline called topology. So a common metaphor for topology is rubber sheet geometry. So in topology, we deal with geometric objects, something like a circle, but we kind of imagine that the circle is made of rubber, so it can be stretched, squeezed, and so on and so forth. So in particular, a circle can be continuously deformed to, say, a square can be deformed into a triangle, so all of them can be deformed into something like this. So all these shapes are the same from the topological point of view. Right? So maybe later you can watch these two videos. So now I'm going to just show you a picture from one of these videos just to make a point, right? So here you can see a series of images illustrating that a cup can be continuously deformed into a donut, right? And because of this, we have this sort of topological joke, right? The story goes like this. So there was a topologist. So he was drinking tea from a clay cup, right? So suddenly the handle breaks off. Very strange, says the topologist. The shape of the cow is now completely different, but now one can still drink tea from it, right? So because there is no handle, so from the topological point of view, it's a different shape. And then he continues drinking, and now the bottom of the cup drops off, right? And if the bottom of the cup fell off and the handle fell off, then essentially, so in the beginning, you know that there was something like this, cup with a handle, right? So, but now there is no handle and there is no bottoms. So essentially, this is a cylinder, something like this. And now the shape is back to the original one, but one cannot drink tea from it anymore. Okay. So topology has a lot of applications in physics, biology, robotics. I know that a lot of you are doing physics, so you probably will want to dig deeper into topology in future. But now, let me just say a few words about a recent modern application that just arose probably around 10, 15 years ago, topological data analysis. So in topological data analysis, what we do is something like this. So if we have some points, observation points scattered in some space. Well, let's say for simplicity, if we have some points on the plane, right? So imagine the first situation. So these points are just kind of scattered around some area. And another situation when these points are scattered around something like a circle. Well, and maybe a third situation is when we have some points that are scattered around something like a figure 8 shape. Right, so here is just like an area. Like here it's just like just an area. So here is just something like this, 2 holes, and here is like something like a circle, right? So in topological data analysis, we develop tools that allow us to distinguish these situations. So tell one from another, and to kind of detect the topological shape of this figure that our data is sort of scattered around. Now, and it works even if our data lives in, I don't know, 100 dimensional space that we cannot really plot in. we can detect really complicated shapes with these tools. What this is used for is a different story, but it is just to give you some idea of how topology can be applied in real life.